Hello everyone, welcome to the OneClass channel. My name is Millan and I am a software engineering student at Carleton University in Ottawa, Canada. Today, I will be going over some commonly asked physics questions at both the high school and college or university levels. If you're interested in getting help with your homework or if you're interested in tutoring, check out the links in the description below. Cool, so I'm going to switch over my screen real fast. Looks like the right one. Okay, cool, and let's get this physics party started. Okay, so the first question that we got on the menu today is asking us, how can we convert tablespoons to grams? Okay, so a tablespoon is, hopefully you've seen one before, a spoon. Now, tablespoons are usually used to measure volume. So I'll write that out. Tablespoon. This is a unit of volume. And 1 tablespoon is equal to 15 milliliters. 15 milliliters. That's maybe like, if you were to spill something, that could be about 15 milliliters. So that's just thinking about like, what you could expect in terms of volume. Maybe like the volume of a grape might be like, or maybe like a handful of grapes could be like 15 milliliters. Yeah. Okay, so that's 1 tablespoon, 15 milliliters. But grams is a unit of mass. This is a unit of mass. Okay, so, and its symbol is G, lowercase g for gram. Now, can we directly convert volume to mass? Not quite, but if we know the density of what is making up the volume, so let's say we have a tablespoon of maybe water that's going to have a certain density, then we can put that on a scale and determine its mass. But if we had something like a tablespoon full of liquid metal, that's going to be much higher in density. That's going to be a lot higher in terms of mass. So if you wanted to convert tablespoons to grams, you would do it like this. It's kind of like a unit cancellation type of method. So you would take your volume, multiply it by density to give you mass. Okay, now perhaps our volume, or they say they want to convert tablespoons to grams, so tablespoon, that's the volume, that's equivalent to 15 milliliters. That's just to be more, to use a more common unit, because of course you could also write it as like, this is equal to 1 TBSP, tablespoon, but generally milliliters, grams, and all that are generally preferred to be used as units of measurement. Okay, so for volume, we're going to have 15 milliliters. Density, we're going to have, depending on substance. Actually, density is typically represented with the letter P. So let's just put that P substance, which is grams per milliliter. And that is equals to 15 times P substance not substance, whoops, substance, because we don't know what it is. It could be water, it could be liquid metal, it could be hot sauce, and we have grams. Okay, P substance, I'll just specify that to make it extra clear. This is going to be the density of the substance of interest. Okay, so let's run through an example and put that through the equation, and we can see how this works out. So we know that the maybe if we did water, water density. So this would be like it'd be P, the density of H2O. H2O is good for you. Make sure you stay hydrated. Drink your water on the regular basis. I know it's about 1 gram per milliliter. Now, that's a pretty good approximation. Of course, like it depends on the temperature of water as well. But let's just use that 1 gram per milliliter. So if we put this into the equation, we have 15 milliliters multiplied by 1 gram per 1 milliliter. You see how the milliliters on the upstairs and the downstairs, they neutralize each other, leaving us with just 1 times 15, so that's just 15 grams. So a tablespoon of water, assuming the density of water is about 1 gram per milliliter, it's going to be about 15. Now let's say we have maybe a different density, something else. Let's say, let's say we have a tablespoon of pie. You'll see what I mean. So let's say we have pie density. And let's say the density of our pie is p pi is equal to 3.14 grams per milliliter. Okay, if we wanted to find the mass of a tablespoon of pie, we would largely do the same type of procedure. So we'd have like 15 milliliters multiplied by 3.14 grams divided by 1 milliliter. In the exact same way, the milliliters down there and up there, they neutralize each other. I know it said that completely backwards, but you see what I mean. And then we're going to have 3 times, or 3.14 times 15 milliliters. And then we're going to have 47.1 grams. So you see, this is more than triple the mass of a tablespoon of water as a tablespoon of pie. Of course, pie is not a real substance. It's just to show that sometimes you're going to see a little bit more not so easy numbers with your densities, but you treat them the same way. As long as the numbers add up, everything should be good. And you can see, like, more than triple the density, you'll have more than triple the mass of when you put this all together. So yeah, tablespoon, generally you want to convert it to milliliters, and then if you want to convert it to grams, you're going to need to know the density and of what you're measuring, and generally you're going to know what you're measuring. They're not going to be like, what's a tablespoon of in grams? Like, they have to tell you what's in the tablespoon. So yeah, just make sure you know the density and then multiply that by the volume, 15 milliliters. That'll give you the grams. Okay, cool. So the above solution is good. Awesome. Beautiful. Okay, the next question that we got on the menu today is asking us, what are 3D shapes? So 3D shapes, believe it or not, are the 3D and 3D shapes, 3-dimensional shapes. Okay, now 3-dimensional shapes, they're similar to 2-dimensional shapes, except you add a whole nother dimension them. So 2-dimensional shapes are going to sit flat on your plane. So, some examples of 2-dimensional shapes that we're hopefully all familiar with are like triangles, circles, squares, rectangles, rhombuses, hexagons, all that type of stuff. But 3-dimensional shapes, they're kind of like 2-dimensional shapes, but they break into a whole new plane of existence. Okay, so some examples would be like cubes, pyramids. Pyramids are really cool. Egypt has a couple of really cool pyramids. Would love to visit one day. Spheres and all that. And this is particularly, now I know this may seem like extremely straightforward, but in some applications, the 3-dimensional arrangement of objects really can have a lot of impact on the properties of it. Okay, so you're going to see this a lot in chemistry and as well as in physics. That's typically when the 3D shapes are going to be more useful. They have 3 dimensions. dimensions, any point on a 3D shape can be specified by a 3D vector, and these are generally going to be like you know, so perhaps we have an R vector to specify like the position relative to an origin. We're going to have like, you know, Rx in the I direction plus Ry in the J direction plus Rz in the K direction. Okay, so vector formatting for three-dimensional shapes is always going to be possible. You can specify any particular point and you'll have the appropriate vector. You just need to define your axes. So got to define axes. Okay. Yeah. So however you define the axes, it doesn't really matter. Even if you know, you tilt them to a certain angle or you rotate them. Also, you don't necessarily need to have a rectangular axes like these. Of course, you could use polar. You could use cylindrical coordinates, whatever you please. But it simply depends on the circumstance that you need to be analyzing these 3D shapes, that you're gonna choose what type of vector system that you're gonna use to specify the different points on it. Yeah, so I guess in a chemistry sense, the shape of 3D objects really determines a lot of the chemical properties of some stuff. So as we know, water has a dipole. So a water molecule looks like this. We have like our oxygen. Of course, I could have written just O, but I just wanted to make sure that that is clear. And then we have the two hydrogen here in this type of shape. And kind of like one way that you can draw this is like coming forward is like triangular, like this, and going away is like you know, lines like that, and this would be just electron pair, electron pair. So the shape of water is like this. Like, imagine my head is the oxygen, the hydrogens are like this, kind of coming out like horns, and the electron pairs are coming out like my beard and like kind of like a ponytail at the back of my head. So if my head's the oxygen, like we have one axis of these two hydrogens and this direction for the electron pairs, and that's a very particular shape that like these that these water molecules are going to have. And because of this shape, water molecules arrange in a very particular way. So the hydrogen bonds, these hydrogen here, they want to be close to the electron of another water. So those hydrogens want to be close to the you know, electron pair, and you can kind of see like how these could kind of like start to crystallize in a certain way. So these are separated by an angle of 120 degrees, I believe, and you could kind of see like, you know, imagine this: when water freezes, you see like snowflakes. Like that crystallization pattern is all dependent on the 3D geometry of the component molecules that make it up. So because of this like bent shape, this is why we might see like hexagonal snowflakes that look like this. So we have like O, H, H, and then we have like, I mean, an O here, and then like that's H goes there, H goes there, H, O, H. And I mean, you can kind of see how that pattern would proceed. Maybe I should finish it off. And yep, so that'd be like that. O and H, and I think 1, 2, 3, 4. Yep, and of course, like this would look a lot better had I drawn these oxygens or these all water molecules like the same. But you can kind of see like these hexagon patterns will start to form. This will be like why you see snowflakes. They're always hexagonal, always six-sided. Okay, so yeah, on an atomic level, the 3D structure of molecules is very, very interesting and has a lot of impact on the actual properties of this. So because water is very, arranges in this pattern, that's why we see snowflakes are always hexagonal, because that's just the way that their internal molecular shapes are. Okay, so that's real cool. It's kind of going a little bit into chemistry, but also into physics, because like you see the geometry and how they arranged, and the energy systems that will be required to arrange water like this. Okay, so yeah, the above solution is good. Okay, so the next question that we got on the menu today is asking us, what is the weight of a gallon of water? Okay, the weight of a gallon of water. Let's write that out. A gallon of water. Oops, I see that's underneath my face cam. Let me just... Okay, cool. The weight of a gallon of water. Okay, so we know that weight is equal to mass times acceleration of gravity. Oops. Acceleration of gravity. Okay, and we know that the acceleration of gravity is 9.81 meters per second squared. That's here in SI, and we're going to need to find the mass. I need to find mass of 1 gallon of water. Water is my favorite beverage, by the way. Remember to stay hydrated. You know what the old saying goes: if you're dry, you cry. So you don't want to cry, of course. So let's convert 1 gallon into liters, because we know that the density of water, well, we know in terms of SI units, and since they asked us in gallons, we should convert it to like cubic meters instead of gallons, just so that it'll be easier to use our SI density, which is very nice and clean, 1,000 kilograms per cubic meter of water at standard temperature and pressure. And that's going to be a lot easier to deal with than, of course, like the gallon based density number. It's not going to be just a nice easy 1,000. So let's convert liters of water to cubic meters instead of gallons. So we got 1 gallon. And to convert gallons to meters, not meters, liters, it's gonna be 3.785 liters divided by 1 gallon. Okay, so you see how the gallon up there and down here, they neutralize each other, but liters, we want cubic meters, right? And we know that there's 1,000 liters per cubic meter. So 1 cubic meter, 1m cubed, is equal to 1, or divided by 1,000 liters. That's the conversion factor. And you can see the liters down here and the liters up there, they neutralize each other. So we have, for cubic meters of water, we have 3.785. And divide by 1,000, we can rewrite that divide by 1,000 as times 10 to the negative 3 meters cubed, cubic meters. Okay, so this is our volume of water. In SI. Okay, so we know that the mass is equal to density, which is P, often used by P, so that's density. I'll write that in. Density. Now, why is P used for density, even though the word density doesn't have the letter P in it? Because we said so. And, you know, sometimes, a lot of the times, the letters that we use to represent values don't make a lot of sense. You kind of just have to deal with it. I mean, we would love to go back and change it to be so that every letter corresponds nicely to the value that they represent, but we don't want to unwrite thousands of years of history of people using this. So that's why we proceed to use letters even if they don't necessarily make sense. Like density, not a single letter P in there, but I guess if you flip the D upside down, it looks kind of like a P. Okay, so our mass, M, that makes sense, is equal to P multiplied by V. And that's our volume, which comes from here. Okay, so you can see that our mass is equal to, our density of water is 1,000 kilograms per cubic meter. 1 cubic meter. Multiply that by the volume, which is 3.785 times 10 to the negative, whoops, let's make that 10 a little bit more beautiful. 10 to the negative 3 cubic meters. Multiply them together, and you see the multiply by 1,000 and the times 10 to the negative 3. Those 10 to the negative 3, that's the same as divide by 1,000. So you have a multiply by 1,000, divide by 1,000. They neutralize each other. Also, the units, meters cubed down here and up down here, those neutralize each other. So in the end, we'll just get 3.785 kilograms. And that's 1 gallon of water. Is that what they got? Yeah, that's precisely what they got. Now that we have our mass, so this is the mass of water. Mass of 1 gallon of water. We want to convert that mass into a weight force. So we know that our weight force is equal to mass times gravity's acceleration. So that's the mass, and G is gravity, so that's 9.81 meters per second squared. Okay, so W for weight, that makes sense. Let's put that equation together. 3.785 kilogram, multiply that by 9.81 meters per second squared. And let's ask our good friend the calculator, what is that answer? Okay, so 3.785 times 9.81, all of that is, our weight force is 37.13 newtons. Okay, and yeah, kilogram times meter per second squared is newtons. Oh, I guess here in the answers they use 9.8 instead of 9.81. I prefer 9.81 because I like the precision, and I suppose that we should be using 3 significant figures because 9.81 was our limiter for significant figures. So that's going to be, whoops, zoom it back in. So to 3 sig figs, because of G. So we're going to have weight is equal to 37.1 newtons. Okay. So yeah, the above solution is good. Watch out for sig figs. Isn't this cool? Like all this unit breakdown stuff. So yeah, you just got to make sure that you do it with the proper density value. And I mean, you could just directly do a you know, if you had a gallon based density value, but off the top of my head I don't really have that, and I don't live in the US, so I don't really know what a gallon is. I always think like I always got to convert it to liters to make sense of it. So it is what it is. Yeah, we just got to accommodate all the different units of the world, even though it would be a lot nicer if we all use the same unit, but that would be way too easy. So units. Okay, so the next question that we have on the menu today is asking us, what is the pH of salt and vinegar? Okay, so let's actually think about this for a moment. What is salt? So salt is typically an ionic compound. Typically an ionic compound. And an example, by ionic compound, I mean like we have like cation plus anion together. Cation and anion combination. Okay, now we're typically going to get something like, or an example of typical salt. NaCl, sodium chloride. That's generally the salts that you use, like, you know, when you're cooking, when you're eating. If you I like salt and vinegar chips, so this would be like I would expect this would be like some of the salt that they're using is sodium chloride. So this is an example of salt. Okay, now let's think about this clearly. There is no hydrogen or oxygen in this chemical formula, or yeah, I guess chemical formula. And we need those hydrogen and oxygens are required for anything to have an effect on the pH. Okay, so because there's none, this results in no impact on pH. For the most part, like this for like this particular example, of course, you do have some different types of salts that have some impact on the pH, being like if they do have other hydrogen or oxygen atoms inside of them. But in general, those are generally rare, and they will typically be advertised like, okay, this salt is acidic, you add this to a liquid and it's gonna be more acidic, so that's gonna be more low on the pH. So when pH goes down, that means acidic. When pH goes up, that's basically. Okay, and yeah, so you see, salt generally does not have an impact on the pH, so they're neutral. No impact on pH, neutral, pH 7. Of 7. Okay, that's cool. But vinegar, on the other hand, generally we actually recognize that vinegar is an acidic, or is an acid. So vinegar is acidic. Acidic for sure. As in, like, you know, generally things that are acidic don't feel good on your skin. Generally, you do not want to be taking baths in vinegar. Sometimes people use vinegar as a cleaning product because of its acidity. It helps remove some like tougher grime and other types of dirty things that are tougher to clean with just water. So it's acidic for sure. Its molecular structure looks like this. I'm pretty sure it's CH3 Chaku. That's like how I would like to say it, Chaku. And it's going to look a little something like this. So it's going to be carbon, hydrogen, hydrogen, hydrogen to another carbon. There's a double bonded oxygen here and a single bond to a H over here. So when this becomes acidic, it is this hydrogen right here. I'll circle out it in a different color. So it's this dude right here. this hydrogen right here, this becomes a hydronium ion. Ion in solution. Okay, so we'll get a little something like this. So we'll have like H to C to H to H to C to O to O. There's a minus there now, and then plus H plus. But we know that H plus is really hydronium, so it like joins in with another water molecule and does this. But this is why vinegar, like this hydronium ion that breaks off of it, I'll actually draw out that it becomes hydronium, so that'd be like H3O plus, H3O plus, and this is what causes acidity, and pH is going to be less than 7 because 7 is neutral, more than 7 is basic, so it's got to be less than 7 for acidic. Okay, and yeah, and that's just caused by the hydronium ion that breaks off here. So I guess it's more in the chemistry world than the physics world, but you know, they are tightly related, and I find them both very cool. So yeah, vinegar generally has a pH rating from 3 to 4, which is less than 7 as we expected. And yeah, so vinegar can be a strong acid. Definitely don't take a bath in it. It could be bad for your skin. So keep that in mind. Nice. Is good. Okay, cool. Okay, the next question that we got on the menu today is a little bit of a longer one, but I think it could still be a lot of fun. A whole lot of fun. How could you not have fun doing homework questions? Okay, so we have Alicia Graves Ortiz invented the elevator brake in the mid-1800s, that's a long time ago, making it possible to build tall skyscrapers with fast elevators. Today's skyscrapers are a large fraction of a mile tall. That's very tall, a lot taller than I am. For example, Taipei 101, that's in Taiwan, in the city Taipei. It has 101 stories and is 515 meters tall. So that's a half kilometer. It would take me maybe like 1 or 2 minutes to run. Like if that height was a horizontal width, it would take me like 1 or 2 minutes to run that. So that's it's quite tall. Top speed is 3 times greater than the ascent rate of a commercial jet plane. So that's quite fast in terms of maximum speed that you can rise. That's interesting. And the position of time and the position in time data is here in this table for the elevator. Okay, so it's asking us to make a position versus time graph for the elevator given all of this data. Okay, so conveniently, it tells us the stories and like its position in stories, but we need to like kind of break that down into like you know, a meter or like a more common unit of measurement, because like a story, you know, how long is a story, how big is a story? In some buildings it could be, you know, 3 meters, in other buildings it could be 5 meters, you know, a story book might be 2 meters. Like we have to be more specific with what units are. So we know that for this particular tower we have 101 stories. So it's Taipei 101. I've never been to Taipei, but I would love to one day. Taipei 101. We got 101 stories. And we have 515 meters of height. Okay, so the height per story is going to be like this. I guess I should have probably wrote them the other way around, but if we do like 515 meters divided by 101 stories, we will get 515 divide 101. We will get 5.0 Let's just round that to 5.1 meters per story. Now this is an approximate value because some stories will be larger than others, and the total height of the building, like a lot of these really tall skyscrapers generally have like very tall spires on top of them. So imagine if I had like, if I put like this water bottle on the top of my head and I said, okay, like normally I'm 6 feet tall, but with this water bottle I'm 6'6". So if I wear this on my head and I say that I'm 6'6", some people are going to be like, I guess so, but your actual usable height is not that. But let's just incorporate the spire height, even though it would not be particularly accurate, and we will probably get overestimated speeds. But we would just need to like keep that in mind as we proceed like through these calculations. Okay, so it's asking us to make a position versus time graph, but let's see if our junior tutor here has done that, because it's quite tedious to type all of this in and then graph it. Yeah, so here they've done the conversion. They came to the similar conclusion, 5.1 meters per story. Sounds about right. And so they got the following table, and to graph it, you can see that your distance versus time is fairly linear. Okay, so that's another fairly interesting thing, is because you see between about maybe like 7 seconds and 27 seconds is pretty much a straight line. You can see like that is the slope of that is probably going to be like the maximum velocity that it's going to have at a given point in time. Okay, cool. So yeah, this would be what a distance time graph looks like. I'm not going to do that like on my Microsoft Paint, because Paint would remove the T and just be pain to do that, and it's quite tedious to do this. But you kind of get the general gist of this. There's going to be Microsoft Excel or other spreadsheet software is probably the best way to deal with something like this. Or if you're really into software, you can write your own code to do this. Maybe Python, Matplotlib if you're more in the programming world like me. But that's up to you. Now describe the motion of the elevator in words. Okay, so basically looking at the time graph, describe it in words. Well, initially at the bottom, so distance is the height, and you see I guess here it's only going up to the 90th story, but there's 101 in total, so I guess we're not going all the way to the top. It's like we're going to the penthouse's basement. Okay, so initially it starts off slow, and then it's going to accelerate its the speed of the elevator until it gets to about maybe 5 or 6 seconds, maybe around 7 seconds. That's when the velocity of the elevator is going to be fairly constant, and it's just going to be going up at a constant rate. Now, maybe one of the reasons why you would not want your elevator to be going too fast is, well, if you ever been in like a gondola or in other type of situations, or an airplane, of course, airplanes change their height very rapidly, and you can kind of feel that in your ears, because your ears need to adjust to the changes in air pressure around. And if you do that too fast, your ears are going to be quite uncomfortable. So that's why you wouldn't want your speed to be too fast. Otherwise, some eardrums are going to pop, possibly. And that would not be great, because you'll need to cover those medical expenses as the building owner. And yeah, those are expensive. You don't want to do that. Okay, so yeah, it has, and in terms of the description that we have here, they're pretty much describing the same thing. The elevator moves at a pretty much constant speed, and maybe around 30 seconds or so, maybe just before then, it starts to slow down, probably as it's reaching its final destination. Like, you don't want to be speeding up when you see your finish line, because you don't want to overshoot it. And once you get to about 30 or so seconds, we're found our final destination, and we're good. Cool. So yeah, and then we're pretty much considered to be at rest, because as time proceeds, and it's kind of represented here in the graph too, where there's like 4 seconds where our position is exactly the same. So the elevator's probably just staying there, letting people get on, get off, that type of stuff. Okay, so that's cool. That's cool, and that's a fairly good description of the elevator in words. Now, the highest speed of the elevator, when is the elevator going at this speed? So when we look at the graph, we're basically trying to find out when is the slope of this graph at a maximum. So maximum speed this is when slope on position, time graph, is largest. Okay, so it might be mirrored on the cam here. I'll actually make my camera a little bit bigger so you can kind of see what's going on. Okay, so this pencil here is pretty much going to represent like a tangent line to the slope. So initially we're starting off pretty flat, and then we're ramping it up, and then this is where we're hitting the linear area, and the linear area is pretty much just going to be the same, and this is going to be like a more than one type of value. And then as you get to the top, well, it's getting smaller. The slope is getting smaller. Like we're getting flatter, smaller slope. Okay, so the maximum speed is clearly going to be in the middle linear area, because that's when it's like the most slopey. Like before that it's flat, and after that it's flat, so it's got to be when it's slopey, when it's the linear area. Okay, so I'll shrink my camera down so I can write some comments about that. In this case, it's the linear region. In between maybe about like 4 seconds and maybe about 30 seconds. Of course, it's kind of tough to tell without vertical lines on the graph, but it's just an estimation. It's going to be in the middle. Okay, so yep, the slope is and I guess they calculated the slope too and I guess my guesses were pretty good, and they came to about 15 meters per second. Seems about reasonable. Yeah, and of course you could calculate that by just like taking the graph here. So slope equation is going to be y2 minus y1. That's the rise divided by the run, x2 minus x1 equals s. So that'd be the slope. Or you could find the first derivative, but we don't have a function here, so it would probably be better to do the other slope method. And yeah. But I guess instead of y they used x and t. So t, the horizontal and on the top is the vertical. Okay, cool. And the last question that they have here is, when is the elevator going at the speed? Of course, it's in the middle, and we would find out with the slope. We're subbing those numbers. Let's actually sub in those numbers just to be sure that we're working good. So maybe let's try about 30 seconds. So y2 x2 is so y2 at 30 seconds is 441.15 meters. 441.15 meters, and that's at 30 seconds. And then y1 x1, that is equal to, well, let's take the one at like about 4 seconds, 4.4 meters, and 4 seconds. Okay, so we're running this through the calculation. We'll have max speed. Max speed is the slope between these two areas. So it will be y2, which is 441.15 meters, minus 4.4 meters, all divided by that was not 4.4 meters. That's 4.4 stories. Okay, so it's yeah, be careful with conversions like that. Yeah, okay, that's why it felt a little bit fishy. Okay, so yeah, 4 stories is 22.44 meters. 22.44 meters, and that's 30 seconds minus 4 seconds. Okay, so let's run that through the calculator and figure out what that is. I expect to see about 15. So Okay, so 441.15 minus 22.44, and that divided by 26, which is 30 minus 4, I get about 16.1 meters per second, which I guess is the same ballpark as the answer that they given from the junior tutor here. It's just the junior tutor, I'm going to assume that, yeah, they incorporated some of the flatter areas. So they incorporated some of the flatter areas of that path, like here, which is why it's going to correspond to a lower average speed over that area. Okay, so it's kind of right, but you know, I've clearly found a velocity that's higher if I change those bounds a little bit. Okay, yeah, so it would be even better to do like a first derivative and to find the maximum that way, but that will take some numerical approximation to get a function out of that. Okay, so the last question, part of this big long section, is asking us what sort of considerations do engineers need to make sure to ensure the comfort of the passengers. Okay, so one of the things that I already mentioned is, you know, when you change your height, your altitude very quickly, the change in air pressure can be quite uncomfortable to the human. So if you've ever been in an airplane and you're not familiar with that feeling, you know, that feeling in your ears is like they're popping. That's quite uncomfortable, and if you're changing your height too quickly, that will be very uncomfortable. And you know, so you don't want to have your vertical speed too fast. Another thing that they mentioned here in the answer is actually a very fascinating thing about the Taipei Tower is they have a they have damping. What I mean by damping is so tall buildings, when they experience a big wind force. So this is a tall building. So this is building. And here we have some wind, some gusts of wind. Windy. You know, the building is going to wobble, wiggle, wobble, which is going to be quite scary for the people inside, thinking, you know, an earthquake is going on. So one thing that is inside the Taipei Tower is they have this massive, like very, very heavy ball. That's like pretty much like pure steel, so this is heavy. And it's like attached to springs and such inside of the building. So that like if there are gusts of wind, the big heavy ball can be moved around inside of the building to counteract the shaking of the building caused by external forces. Typically just wind, but like earthquakes as well, the counterweight inside of the Taipei Tower helps to dampen some of the vibration so that the people inside are not like, you know, getting thrown around. So yeah, that's a very fascinating thing that happens in the Taipei Tower. Yeah, so the above solution is good. This was a very long question, but you know, a lot that we learned here. The above solution is good. Awesome. Okay, okie dokie. So the next question that we got on the menu today is asking us, which of the following vectors has a magnitude of the vector equal to one of the components of the vector? Okay, so let's look at this question and dissect what some of these keywords in the question title are asking us for, and then we can better handle how we should proceed to solve this question. Okay, so following vectors is a magnitude. Okay, now how do we find the magnitude of a vector? We do it like this. I'll write it out. Okay, so we got the magnitude of a vector. So suppose that we have a vector like r. Yeah, let's just say we have a vector r, or maybe v. I feel like v for vector. So the magnitude is sometimes represented like a absolute value, but sometimes people get confused with the absolute value, and sometimes people will write it with double absolute value to specify, like, yeah, this is a vector, take the magnitude of it, and this way there's no ambiguity with absolute value. And to find this, it's very Pythagoras looking. Now I'm going to write the general equation, but generally you're probably only going to see 2 or 3 dimensional vectors, so this will only be relevant for, like, you only have 2 or 3 terms, but you want to have like all of the v terms, v of I squared, and you want to add them all up. Okay, so this is a general equation. But in 2 dimensionals, in 2D, you'll have something like this, like the magnitude of the vector is really just like a Pythagoras type of situation. So you have like the x component squared plus the y plus the vy component squared. And in 3D, of course, we'd have a similar looking thing, except we'd have 3 terms under the root. So the 3 terms under the root are going to be vx squared plus vy squared plus vz squared. On and on and on. Let's say you're deep into the string theory of physics and you're doing 11 dimensions. You would just have 11 squared terms under the root and you would add them up. Okay, so this is how you find the magnitude of a vector. Now it's saying which one of these has a magnitude that is equal to one of the components. Okay, so the another rule that I'll mention, magnitudes are always bigger or equal in size to any one of the individual components. Any of individual components. Okay, that's a nice rule, and magnitudes are only going to be equal if there's only one component. Okay, I'll write that out too. Equals single component in one component vectors, in single component vectors. And maybe it'd be better to say absolute value of the single component value, and we'll see why, particularly when we get to option B. Okay, but let's actually calculate the magnitudes of all of these, and then compare them to the components and see if they work out. Okay, so let's do option A. Option A, we have A is equal to 2i plus 5j. So to calculate the magnitude of A, we'll have the square root of 2 squared plus 5 squared, and that's equal to 4 plus 25, equal to the root of 29, and let's ask our good friend the calculator what that is. So that's about 5.39. So that's about 5.39. Okay, is 5.39 equal to the components? Well, none of the components are like that, so not the same as components. Not the same as components. Okay, so option A is disqualified. Nope. Okay, now let's take a look at option B. Option B looks like this. B is equal to negative 3j. Okay, now to do the formal part of the magnitude, of course you could see that it'd just be like the square root of itself squared, so it should just be one thing. But I guess the formal term, or the formal way to write this out is even though there's no I component written, that implicitly means that there's a 0 I component. So we actually can write that out. 0 squared plus negative 3 squared. And that's just equal to 3. And this would be like the zeroed x component. Okay, now, you know, we have a magnitude of 3. And does that match? Absolute value matches. Abs value matches. Just keep checking. So while you could controversially argue that option B has a magnitude equal to one of its components, we want to still see all of the other options to see if there's something that's like unambiguously correct. Because in these multiple choice type situations, you're only going to be able to choose one of the options. You want to choose the most correct. So if you have one option that's controversially correct and one answer that's concretely correct, always choose the concretely correct. And I think that's what we're going to see on option C. Oh, by the way, you see on the rule that I've written, magnitude is equal to the single component value in a single component vector by the absolute value. You can see that, you know, the case is true here. The single component was j, and the magnitude is just the absolute value of the component, which is 3. Okay. You could negative magnitudes also are sometimes used, but they're more rare. So that's why I would say it's more controversially correct if you were to say 3. But let's take a look at option C. And let's see something that's uncontroversially correct. Oh, I've spoiled the surprise, but here we have plus 5k in the c direction. For the c vector, and let's calculate the magnitude. So k corresponds to the z direction, so we have like 0i plus 0j plus 5k. That's like the full form of this vector. So we could rewrite that as like 0i plus 0j plus 5k. These mean the exact same thing. This is just to show like this could be a three-dimensional vector, but only the z direction is relevant to this particular vector. Okay, so to take the magnitude of vector c, we would do 0 squared plus 0 squared. Honestly, the more you get familiar with this, the less really you need to write like the 0 squared, but I just want to be 1000% clear about this. And then plus 5 squared is equal to the root 25 equal to 5. And this is unambiguously the same, like absolutely the same as component. And this is like unambiguously correct. So C would be your best option for this case. Okay, and that's just, even though option B you could argue that it's right, since C is doesn't require arguing to be determined correct, C would be your better answer if you were to actually see this on an exam type situation. Okay, so yeah, I mean, they came to similar conclusions here. They got 3, 5, and it's not equal, but you could argue. Yeah, so the answer is C. So yeah, the above solution is good. However, sometimes negative magnitudes are used, which could make option B controversially correct. We need to debate a little bit, but you know, under the right circumstances, maybe you could argue that. Okay. So the next question that we got on the menu today is asking us, at what temperature will aluminum have a resistivity that is 3 times the resistivity of copper when copper is at room temperature? Okay, so we know that the resistivity is basically how much resistance, it's kind of like resistance density. So resistivity There are a couple of different versions of resistivity, but the most simple one is going to be resistance per unit length. Okay, so this will generally be ohms. Oh, let's make that ohm a little bit more beautiful. Ohms per meters. Higher means more resistivity. So something like rubber. Rubber is going to be rubber has a lot of resistance, so it's going to have a very, very large resistivity value. But something like copper is used in wires because it famously has low resistance, low electrical resistance. Something like copper would have a fairly low resistivity value compared to something like rubber or other insulating things, maybe glass, or I guess glass could kind of be a good conductor. But anyways, the next part is we want to have this. We have this equation right here, which is the resistivity equation that is at different temperatures. Okay, so there really should be a minus there. So the official equation looks like this. It looks like a minus. I guess you could use resistance, or you could use resistivity. It really is the same thing. Once you multiply a particular distance in there. So like this could be like the length of a wire, or would be like the distance that you multiply by to get the actual resistance value. Okay, so the equation that we're going to use is pretty much the same as the one we use here. Is just for some reason the minus is not showing. That's not great, but it is what it is. Okay, so we got resistivity. Oops. And let's write that this is represented with symbol P. With symbol P. Why? Yes. Because we just needed a letter. We're pretty much picking letters at random at this point because there's not enough letters to have a letter that corresponds properly to the name of the thing that we're representing. So P, resistivity final, or resistivity at TF is equal to RO. So this is resistivity at initial temperature multiply that whole thing by 1 plus alpha multiplied by the final temperature minus the initial temperature. Final temp, initial temp, and 1 is just a 1, and the alpha value, we don't have it here, but what it really represents is the temperature coefficient of resistance. Temperature coefficient of resistance for conductor. Okay, so that is dependent on the particular conductor that you're using. Like something like aluminum might have a different value for alpha as opposed to something like copper or something like zinc. All those different types of metals are most likely going to have different thermal or different temperature coefficients for the resistance. Okay, and the question is asking us, at what temperature will aluminum have a resistivity that is 3 times the resistivity of copper at room temperature? Okay, so first we're going to need to know the resistivity of aluminum as well as the resistivity of copper. So here we have the resistivity of aluminum. So P aluminum AL represents aluminum, is 2.81 times 10 to the negative 8 ohm per meter. Wow. At 20 degrees Celsius. That really should be ohms per meter in resistivity, unless we're actually using resistance values. Like, it could be for a standardized length, but generally for resistivity, you're going to need ohms per meter. So I'm going to need to, I'll need to mention that later on. And the density of, the resistivity of copper, Cu, for copper is 1.7 times 10 to the negative 8 ohms per meter. And this is also at 20 degrees Celsius. Okay, as you can see, copper has less resistivity than aluminum. So copper is a better conductor, which is fair. I guess that's something we could expect because copper is so commonly used in wires and that type of stuff. Okay, so, and it's asking us when it's the triple of our copper. So that's going to be our final resistivity that we're trying to get. So our P final, our final resistivity is going to be 3 times the density of copper, which is going to be 3 times 1.7 times 10 to the negative 8 ohms per meter. And that's equal to 3 times 1.7 equals 5.1 times 10 to the negative 8 ohms per meter. Okay, cool. So this is our final resistivity value, and our what's our AL value? Our alpha value is going to be our alpha value for aluminum, because that's one of interest. It'd be great if they mentioned that previously, just on its own. Gonna assume that's gonna be 1 or 3.9 times 9 times 10 to the negative 3, and that should be a 1 over Celsius, or 1 over degree Celsius. Okay, so let's take a look at our initial equation, and what we're trying to solve for is, well, now that we have our final resistivity, we have our initial resistivity, and we have our initial temperature, 20 Celsius. Those are what our initial resistivities are, and we know that we're trying to get 3 times the resistivity of copper to be our final, and we're just trying to isolate for TF, the final temperature, so that this equation will hold. Okay, so we have P final is equal to P naught, or the initial thing, the initial P naught is the initial resistivity, and then we have TF minus T naught. Okay, so PF, we found that to be 5, or okay, let's first isolate TF before we sub in our numbers. Generally, that's the better way to go about things, because calculators are where your problems come from, like if you just type in a number wrong. So if you set up your equation right, generally you'll be able to still get like maybe half marks, even if your calculation numbers are wrong. But if you just like sub in the numbers now and try to isolate them, yeah, it could be quite painful. Okay, so to isolate TF, we're first going to need to divide both sides by PO, or P naught. This is equal to 1 plus alpha of aluminum times TF minus TO. And then we're going to PF over PO minus 1. And that's equal to alpha of aluminum times, oops, not I, multiplied by TF minus TO. Okay, and then we're going to do 1 divided by alpha of aluminum multiplied by PF over PO minus 1. And that will be TF minus TO. And then to isolate TO, to isolate TF, we just got to add both sides. Both sides need to get TO added to them. So it's going to be 1 over alpha AL PF over PO minus 1 plus TO is equal to TF. Okay, our alpha AL value, 3.9 times 10 to the negative 3. Okay, so 3.9 times 10 to the negative 3. Okay, and our PF value was 5.1 times 10 to the negative 8. 0.1 times 10 to the negative 8. I guess the units don't matter because we're just dividing by something else that's the same units. Our PAL number. Why did I write 0.81? It should be 0.82. Whoops. Okay, so it's 2.82 times 10 to the negative 8, and this is subtract 1. And then we're going to add 20 Celsius to this whole thing. And this will be our final temperature. Okay, so let's ask our good friend the calculator how to figure this out. So we're going to have 5.1 divided by 2.82. You actually don't need to see how both these terms have times 10 to the negative 8. Well, those two just cancel each other out. So it's really just 5.1 divided by 2.82. And then, so that's like 14 for me. Whoops, not. I multiplied them, not divided them. That's a issue. Okay, I'm gonna redo that real fast. Okay, multiply that, or subtract 1 from that. Take that number, divide by 3.9 times 1,000 plus 20. And I came to precisely the same answer. Once I put this all in my calculator, 227 degrees Celsius. Okay, which is exactly what the junior tutor got. So that's awesome. Awesome. So this is using this equation for the resistivity and how it changes with temperature. You can calculate different stuff about it. You just need to like kind of decipher where you can get your certain values, like your PO or your P final. That comes from the fact that that's our final target, three times the resistivity of copper. But yeah, so the above solution is good. Solution is good. However, the equation is missing the minus between the TF and TO and resistivity should be ohms per unit distance instead of just ohms. Okay, cool. Okay, so the next question that we got on the menu today is asking us, an incandescent light bulb produces what type of visible spectrum? Okay, so what is an incandescent light bulb? An incandescent light bulb is these classic light bulbs that are this. So imagine this is glass. And then they have like a little wire here, and this wire spins in a coil. And then electricity, let's make electricity purple. I feel like electricity feels purple. So this is going to be like a electric circuit. And this is going to get hot. So hot that it's going to heat up some of the gases around it, and some of these gases are going to make light when they get heated up. Okay, so that's how these incandescent light bulbs work. Electric circuit runs through the filament. The filament gets really, really hot and heats up the gases around it, and those heated up gases, with the electricity going through it, they make light, which is why you can see in the dark. Okay, so visible spectrum, that's the key thing here, is visible spectrum. Visible spectrum. The key word here is humans can see. And for this particular thing, it's for electromagnetic wavelength, the visible spectrum, which is just the subsection of the electromagnetic sphere or wavelength. No, not the electromagnetic spectrum. A subset of the electromagnetic spectrum is the visible spectrum. So this is a couple or a small subset of all electromagnetic radiation is visible. Okay, so if this is low wavelength or low frequency, electromagnetic radiation, it's on maybe this side of the spectrum, and here we have high frequency. And here we have high frequency. Visible light would just be like a little area like this. So this is just a visible light spectrum. Not visible. Visible light spectrum. And it follows the rainbow. So first is going to be red, orange, yellow, green, blue, purple, magenta. Okay, so that's kind of what it is. So now, which does the light bulb produce? Let's actually look at which does the light bulb produce that is visible. Okay, so let's take a look at the first one. Black body radiation is actually tightly associated with infrared radiation. That's the radiation that is lost due to you losing heat through radiation. In general, black body radiation as well as infrared is going to be invisible. Like you can't see, in general, you can't see heat leaving your body. Night vision goggles can, however. That's how night vision goggles can see in the dark. They pick up the thermal signals from the black body radiation and the infrared light, and they transform that, or they translate that invisible electromagnetic radiation into visible light that helps you see in the dark. So over here in the invisible region, we have black body and infrared. These are invisible. And this is invisible. I feel invisible. Okay, so that kind of disqualifies them from being on the visible spectrum, is the fact that, well, they're on the invisible side. Both of them are. So yeah, that's the reason why we have to disqualify black body and infrared. Even though this incandescent light bulb is certainly going to have that type of energy or that type of radiation that is going to be emitted from it, it's just not going to be it's not going to be visible at all. So now we're just left with discrete and continuous. So let's actually describe what the difference between discrete and continuous is. Discrete is like only one value at a time, no in-betweens. So it's like quantized. Only particular values with no in-betweens. with no in-betweens. No in-between values. And then we have continuous. And this is spectrum of values. So a continuous value or a continuous signal could look something like this, but a discrete value or a signal is going to look something like this. Like maybe if you get more into like the computer land, you'll see like computers really like dealing with discrete values because, you know, computers are based in binary, and binary is very well suited to discrete math. But continuous values are more like your everyday stuff. Okay, so the light emitted from the light bulb, the incandescent light bulb, is actually like, it's going to emit light from all different spectrums or all different frequencies, but in the visible light spectrum as well as like in the infrared area. So since there's going to be like, you know, a little bit of red light here, a little bit of green light here, a little bit of blue light here, all of those are kind of like added together to make like the combined light signal that comes out of a incandescent light bulb like this. So because there's so many of them mixing together, and you know, there's no like discrete or not really a discrete signal that like adds up all the different colors, because you know, the wavelength or the frequency could be like in between values. It's more of a continuous type of signal. But you know, if you go deeper into quantum mechanics, you might change your answer on that. That's a nice thing to think about. But yeah, it's mostly continuous because of how much spectrums are added, and like the frequencies, there are in between values until you get to quantum mechanics. But don't think about that too much. So yeah, it's a continuous spectrum. And continuous would include the black body and infrared, as well as all the stuff in the visible. So yeah, the above solution is good. Is good. Okay. So the next question that we got on the menu today is asking us which of the following properties is best used to describe capacitance. Okay, so capacitance is related to capacitors. Believe it or not, I feel like their names are very well suited for that. So capacitance and capacitors. So these are things, these are electric components, electric circuit components that store energy in the form of charges. Okay, capacitors are like this. So there are two parallel plates. There are two parallel plates with charge accumulated on either side. So in your circuit diagrams, your capacitors look like this because that's exactly what they are. Okay, so maybe over here, let's say we have a battery, a plus minus battery here. You would see that a lot of plus charges would accumulate on the plus side of the battery, and you would have an equal amount of minus charges that accumulate on the other side of the battery. Okay, and the voltage across here, so plus minus, the voltage of the capacitor is I think it's V is equal to QC, or Q is equal to CV. So CV is equal to Q. This is the voltage of capacitor. This is the capacitance value. And this is the charge on the plate. Charge on plate. Okay, awesome. So this is exactly what a capacitor is and the type of equation that it has. Now let's take a look at these properties and see which is the most well suited to describing what a capacitor is, capacitance, and that type of stuff. Okay, so the ability to conduct electric current. While capacitance is kind of related to electric current, it's not really the ability for electric current to go through it. In a DC circuit, capacitors actually don't allow any current to go through it, regardless of their capacitance values. You need an AC signal for current to pass through a capacitor. So it's not really that related to electric current, because that kind of also depends on what type of sources you have in the circuit. Okay, the ability to distort an external electrostatic field. They do, to a certain degree, distort their external electrostatic field, but that's generally not the reason why we use capacitors. We generally use capacitors to think about what's inside of the capacitor, like the charges inside an electric field that builds up between the plates. Okay, so the electric field would kind of build up to look like this. So that's the E field. Okay, now the next, so this is not really the case because, I mean, it could distort an external electrostatic field, but that's generally not the reason why we use capacitors. We generally use capacitors because they store energy in the form of charge. And that kind of leads us to the next one, the ability to store charge. So that is absolutely related to capacitance. You can see the amount of charge that is stored on the capacitor's plates is the capacitance multiplied by the voltage. And of course, we could rearrange this equation so that we can isolate either capacitance or isolate the voltage. But it is, capacitors store charge, and the ability to store charge is really just their capacitance. Okay. So with the constant voltage, higher capacitance means more charge is stored, and that's should be fairly clear by this equation over here. Okay, and electrostatic energy. Okay, I think one of the words here that is kind of a red flag is electrostatic. This is generally related to static electricity. I suppose this is kind of the case because, like, if you have it in a DC circuit, it is going to have like some static amount of charge there on either one of the plates, and that's just going to stay there. So I guess it could be related, but in the other sense of like thinking about static electricity and how charge accumulates, this is not particularly related. I would say this ability to store charge is probably the best answer for this if we only have to choose one, but the fourth one is also kind of related because electrostatic energy is stored inside just by the accumulation of charge on either side of the plates and the electric field in between the plates as a result of that. Okay. Yeah, so here we have the equation, like capacitance is dependent on the charge and the voltage across it. Another equation for capacitance is the area of the plate divided by the separation of the plates multiplied by epsilon naught, which is the permeability constant of free space. So this is how permeable or how well that electric field is going to be able to exist between the two plates. Like, it's going to have a different value if there's air between the plates. Sometimes you might have some other dielectric materials, maybe something like some types of plastics you might want to have in between the plates, and that could give you different electric properties that, you know, could be what you want depending on the application that you're using it for. Okay, so yeah, the ability to store charge is the best way to describe it. Yeah, so the above solution is good. Above of solution is good. Capacitors. Okay. So the next question that we got on the menu today is asking us about circular motion. In circular motion, a tangential acceleration can can change the magnitude of the velocity, but not the direction of the velocity. Explain why that's the case and explain what's going on. Okay, so let's actually, that's a great diagram, but let's actually draw one ourselves so we can kind of go through this and have like kind of a step-by-step explanation of what is going on with tangential acceleration. So they said in circular motion, and that's the key point here, we have to have a circle for motion to occur in. So that's a pretty good circle. Maybe just about here is the center. Maybe this is the radius. Actually, not maybe. This is definitely the radius. And suppose that we have, if we want to make this more of like a real life situation, we could kind of imagine that, you know, if we're a car driving in a roundabout, that's a circular motion type situation. And yeah, so like this. So maybe this is us in a car, vroom vroom. And we have a this is our current velocity, but of course at different areas or different parts of our path, we're going to have our velocity is going to be still tangential to our path, but it's going to be pointing a different direction. So if we get to this area, we can see that our tangential velocity is going to be it's going like pretty much the opposite direction of where it was going before, but still along the circular path. And I guess over here, it's a similar type of story. The magnitude might be the same, but the direction is clearly different. Okay, now so when we have tangential motion, we have two types of accelerations that are possible. Okay, when we're in circular motion, we have this acceleration along this path. I'll put that in a whole different color just to make it a little bit more clear. So this is going to be a centripetal acceleration. That's one. And we always have another one, which is tangential acceleration. Okay, now so I'll actually write out what they are. So this is tangential. Oops, looks like my webcam is covering that. I'll shrink that down a bit. Okay, cool. So tangential acceleration. AC is centripetal acceleration. Okay. Centripetal acceleration is always going to be towards the center. AC. Centripetal acceleration is always towards the middle point of the circular path. And tangential acceleration, well, it's always along the tangent line. A tangential and acceleration of the tangential. Okay, so let me just write some comments. AT and AC always perpendicular to each other. Always perpendicular to each other. And AC always towards center of circular path. And AT, oops, not A times T, A subscript T, always along tangential path. Always collinear to tangential velocity. Okay, so it's always along the same line of the tangential velocity, and we know that the only reason that the velocity is changing direction, so you see at the top here, it's like you know, towards the northwest, and then here it's down towards like the southeast. The only reason that the tangential velocity is changing is because of the AC, the centripetal acceleration. The tangential acceleration controls the speed at which you are moving around the circle. Okay, so if we were going back to our driving in a roundabout situation, if I hit the gas on the car, and I'm gonna see like my speed is gonna increase, but you know, my path is, if I just hit the gas, I would need to I guess I would need to like sharpen the turn of the steering wheel to make this more tight to like maintain that circular path. The acceleration, tangential acceleration would need to increase a little bit. But changing the tangential acceleration alone is not going to change the direction of the velocity, because, well, we have like, maybe this is our car and this is our velocity here, and this is our tangential acceleration and maybe our centripetal. So because they're collinear, because V and AT and tangential acceleration are collinear, tangential acceleration cannot change the direction of the velocity. Okay, and that's just because they are collinear to each other. Of course, AC, the centripetal acceleration, is definitely going to change the direction of the velocity, but AT, yeah, that's not going to change the magnitude of the velocity because they are collinear. Okay, yeah, and it's just make sure that you always know that acceleration, centripetal and tangential are 90 degrees separated, and how they're going to look with respect to the circular path that you're taking and your velocity. Okay, so yeah, it's great stuff to know. Circles, circular path. It's a pretty nice diagram, can't lie. So yeah, the above solution is good. Yeah. Okay. So the next question that we got on the menu today is asking us, two charged particles that have an equal magnitude of charge are located on the y-axis according to this diagram. I'll redraw the diagram in a minute just to make it a little bit more clear. And it's asking us, at any point on the x-axis, how can we find an expression for the potential? Okay, so I'll redraw it to make it a little more clear. Suppose we have Q. That's very cute. Ha, funny. And here we have our x-axis. Here we have A. Here we have an equal distance A. And this is our y-axis. And here we have our x-axis. So suppose that we're here. X. Find potential. Find electric potential, to be more specific. Okay, so the equation that we have for electric potential is KQ divided by R. Yeah, exactly. So electric potential is V, typically means voltage, but it's better to say electric potential in this type of situation because we like to reserve the use of the word voltage for more electric circuit situations. So in these type of situations where it's like we're talking about individual charges, we talk about electric potential. So it's better to say electric potential instead of voltage for this type of situation. Okay, and this is KQ over R. And K is equal to constant. Leave us 9.09 times 10 to the 9. Yep. Q is the charge. And R is the radial distance. Okay, so the radial distance R is actually going to be something like this. R. And we know that since A is the same for both of them, they're gonna have the same R value. So hey, R is really just a if we have A and we have X, they are at an angle like that, and we have R here, so we know that R is equal to the square root of A squared plus X squared. Okay, so that will be our R value just by looking at the geometry here. Like, it is possible that X is 0, but if X is equal to 0, we're just going to have R is equal to A, and that would be perfectly reasonable. Okay, so yeah, awesome. That's great. That's our electric potential R value. Our Q value, well, that's really straight up given to us there. Well, they don't give us a value, but it's just Q, and because the big Q that we're using here is going to be the little q here. So now we just need to think about here. So if this is our point P, our point of interest, our P point for a point of interest, the potential at P is, so the voltage at point P is equal to the sum of all K, Q, I values over Ri. So we have to add up the potential contributions from all of them. And so in this case, it's just going to be KQ, or let's use big Q because that's what I wrote on the diagram. KQ over, well, this will be the top one. So this will be the top. And the R value here is root A squared plus X squared. And we found that with Pythagoras' theorem. Now we have to consider the bottom one. So we still have the K, and it's the same charge, Q. And what's the R value for there? It's precisely the same. Precisely the same. It's still it's the same right angle triangle, but flipped upside down. So we have the same A squared plus X squared down here. Now, are there any other charges that we need to worry about? Nope, it's only just these two. So we can try to simplify this equation. So the electric potential at point P, the point of interest that we're measuring at, well, we have the same thing added to itself, so we can just take multiply it by 2, or we can, yeah, I mean, it really is just like multiplying by 2 instead of adding to itself again. So we can just do 2KQ over A squared plus X squared. This is electric potential at point on the x-axis. Okay, ain't that cool? I'm pretty sure. Hopefully we'll see that the answer here has the same result. You could sub out K for 9.09 times 10 to the 9, but sometimes it's better to leave it as a constant if you're not actually going to do the equation. yeah, just to keep everything clear. So yeah, they came to precisely the same answer, and that is awesome. So the above solution is super cool. The above solution is good. Okay. So, the next question that we got on the menu today is asking us, what is an average force? Average force. Okay, so an average force, it also depends on what type of situation are you asking for the average force. So, like, if we're asking for like kind of if we just have a list of 10 forces, find the average force, you add them all up and divide by 10. But that's generally not what you're going to be doing when you have an average force. An average force is generally going to be like, if you have a mass that increases its velocity over a certain period of time, what was the average force exerted on it? So often questions where a mass changes velocity over a given period of time, often questions where a mass changes velocity over a given period of time ask for average force. Okay, that's maybe the most common type of question where you will be asked on determine the average force. And let's see what we got in the explanation here. Force and momentum are tightly related. So P is the momentum. The average force is also equal to d over dt of the momentum. Okay? Yeah. So they say the mass of an object multiplied by the average velocity over a definite time is the average force. It should be change in velocity. I'm going to write that fast. Should not multiply the average velocity, should instead multiply by the change in velocity to get average force, just so I don't forget it later. Okay, yeah. So, and it's got to be over a change and stuff. Okay, so let's actually run through an example of like where we would calculate an average force. Okay, let's say for this particular example, we have a golf ball. A golf ball at rest makes contact with golf club. I've never actually played golf with golf club for 0.0001 seconds, because I mean, even if you are just hitting it momentarily, there is a moment where they are in contact. So if it's for 1/10,000th of a second, and ball flies away at 100 meters per second, it's quite a fast ball. Find average force. Find average force. Ball is 0.1 kilogram. 100-gram ball. That's probably pretty heavy, but you know, this is my reality where I've never played golf, and golf balls can weigh that much. So, or can have that much mass, and because I'm the golf champion of this universe. Okay, so let's figure this out. So the golf ball, so initial velocity is it's the mass. So we want to take the force of average is equal to the change, or the mass times the change in velocity with respect to time. So the change in velocity over time. Okay, so the mass is 0.1 kilogram. Our velocity, well, our initial velocity is, it's going to be final minus VI, minus initial, over the time, which is 0.0001 seconds. And we know that the final velocity is 100 meters per second. So F average equals 0.1 kilogram multiplied by VF, which is 100 meters per second, minus 0 meters per second. It starts at rest, sitting on a golf tee, and over 0.0001 seconds. So let's put that in the calculator. So 0.1 times 100 divided by 0.0001, and the result that we get is 100,000 newtons. And that could be reasonable. Like, that might seem like an extremely large force, but also keep in mind that that force was applied for less than a millisecond, 1/10 of a millisecond. So it would seem reasonable. So that would be an example of how we can use the average force in a question that asks for it. So should set my change velocity. Yeah. Examples of finding average force would be helpful. Okay, so the next question that we got on the menu today is asking us, what is the definition of displacement? Can displacement be negative? And let's address these questions one by one. So the definition of displacement. Displacement. This is the shortest distance between 2 points. Shortest distance between 2 points. So right now I'm in the upstairs of my house. The displacement to disbasement is a straight line down, but my distance, this is not displacement. The distance to my basement, well, that would be like me walking around the stairs in like a curvy path, maybe stopping by in the kitchen, maybe stopping by in the garage. Like, my distance to the basement is going to be different than my displacement. My displacement like pierces through the ground, through the ceilings. Displacement is straight down to the basement, but my distance is going to be like, you know, the path through my house to get to my basement, for the displacement to the basement. Big bars. Yeah, so that's the main difference between displacement and distance. This is specified path. And displacement is the shortest possible path, straight down from me to the displacement. That's a fun thing to say. Now, can displacement be negative? Now, displacement is generally a vector value. And vector values can have a lot of signs, and the signs will depend on how you define your axes. Okay, so signs defined by arrangement of axes. Okay, so imagine that we are chilling on a rooftop like this. This is my house, and we are standing right here. And let's say this is our x-axis, and our y-axis is like this. Okay, so right here we'd have a displacement that would be like that if this is the origin. Now this would have a positive x component, and this is have a positive y component. But you know, if I maybe if that's like a ball sitting on the top of my house, but if I set up my coordinates like this, maybe I'll put them in red, and this is my x-axis and this is my y-axis, and so I should draw that a little bit better like this. So if this is the x-axis and this is the y-axis, you could see that this is going to have a negative x value and a negative y value. Now, which one of these coordinate axes is more correct? There is no answer. Whatever coordinate system that you use is the one that's more correct. So a positive displacement for me standing on the roof could be a negative displacement for a drone or a bird flying around, and for like a ball floating in the air or a balloon. So can it be negative? Yes, but it's what's more important than the sign of the displacement is how the displacement is defined and how the axes of your system are defined. Okay, never be scared of a negative value. That just means, like, you know, if it's the bird's point of view, up here, you know, a negative displacement, a negative vertical displacement is, you know, it could still be above the ground, but you know, as long as we know what the axes are and we know how the axes are defined, the signs are not that useful. Yeah, they just help us arrange ourselves in the sense of our coordinate system. Okay, so yeah, and a lot of the times displacement, to calculate the displacement vector, so displacement is often with r, sometimes with d. Let's say in 3 dimensions we're going to have like a dx in the I direction plus dy in the j direction plus dz in the k direction if we're in a 3-dimensional situation. So sometimes we'll need this will be displacement. Sometimes we'll need the magnitude, which will look like this. So d is equal to the square root of dx squared plus dy squared plus dz squared. And that would be an example of how you can calculate the displacement magnitude. And let's say you have a 2D vector situation. That would just mean that your k term is 0. So you just have a 0 here. And it's just a Pythagoras theorem situation. So it should be fairly straightforward to see from there. And yeah, moving forward and backwards, sometimes that can be represented with positive or negative signs in displacement. But otherwise, yeah, it would seem that this explanation is good. It's just signs are going to be magnitudes are generally going to be positive, so there will be like some negative components. The more dimensions you introduce and the more complexity that you're going to be having these displacement type of situations in. So yeah, displacement can be negative. The above solution is good. Mention of how, actually never mind. Okay, cool, awesome. Okay, So the next question that we have on the menu today is asking us, since velocity is equal to lambda, which is wavelength, times frequency, does the speed of the wave depend on its frequency? So this comes from the universal wave equation. Which is frequency. I'll write it the same way that they have it here. So velocity of wave is equal to the frequency multiplied by the wavelength. Okay, the frequency and the wavelength of inside in a constant medium increasing one will proportionally decrease the other. The velocity of the wave, this is defined by the actual material properties of the medium that the wave propagates through. So this depends on the medium that the wave propagates through. Okay, so some examples are like 3 times 10 to the 8 meters per second is speed of light. In vacuum, but the speed of light in other compounds, speed of light in water, glass, acrylic, ice, etc., is slower than this. Okay, and so that depends on the medium that the wave is traveling through. A light wave traveling through the vacuum of space is going to have that speed, but it's going to slow down when it's traveling through more intense, more dense mediums. Like glass sinks in water, so glass has more density than water. I would assume that glass has a slower speed of light inside of it than water, but yeah. So the velocity of a wave depends only on the medium, not on its frequency. So if you increase the frequency in the same medium, so let's say we're in a space light show and we're shining lasers off into space. If I change the frequency, the velocity is always going to be the same. So the wavelength has to go down for the frequency to go up for the velocity to stay constant. Okay, so that's kind of how the universal wave equation works out. The velocity of the wave is defined strictly only by the medium and the type of wave as well. So like these are light waves, but sound waves, so like speed of sound, so this is about 300 plus meters per second, just around 300, between 300 and 400 meters per second, but it is temperature dependent. So on hot days versus cold days, the speed of sound is different. So that's like physical changes to the medium, and that's going to change the V, but it's not the change in frequency or the change in wavelength. It's the change in the medium that changes V. Okay, so it does not depend on frequency. Wavelength depends on frequency, and frequency depends on wavelength, but the speed is determined by the properties of the medium and the properties of the system. That is exactly the right answer. Absolutely nothing wrong about that answer. So the above solution is good. Awesome. Good job, solution. Okay, so the next question that we got on the menu today is asking us, find the angular speed of Earth's rotation about the axis, and how does this rotation shape the Earth? Okay, so let's first talk about part A. So it's asking for the angular speed of Earth's rotation about the axis. So let's talk about angular speed. Angular speed, aka, sometimes you'll hear it said as angular velocity. They generally mean the same thing. Okay, so this represents the change in angle with respect to time. Represented by the Greek letter omega, by omega, lowercase omega, which I know it looks like a W. Do not, under any circumstance, call this a W. You will get in trouble, because we do use W for other things like work and stuff like that. So we use omega, kind of how this is not W. W's are more like, straight liney. Omega is more curvy. Okay, so and its units are radians per second. Rad per second. Okay, so the angular speed of the Earth, we know that the Earth has so we need to find the time that the Earth takes to do one whole rotation. So one whole rotation (2 pi radians). Now we know that this happens once per day on Earth. Happens once per day on Earth, and 1 day equals 24 hours equals 24 hours multiplied by 60 min per hour, and that will neutralize the hours. It's just doing a quick unit cancellation analysis. And then how many seconds are in a minute? We got 60 seconds per 1 min. So the minutes neutralizes the minutes up there, and we can ask our calculator. 24 times 60 times 60 is 86,400 seconds. And I've seen that number before, so I don't really need to verify it. I know for a fact that's got to be good. 86,400 seconds. Okay, so the angular speed of Earth is equal to, let's call that omega E. I know that looks like we, but it's omega E, E for Earth. It's going to be equal to one full rotation, so 2 pi radians, divided by 86,400 seconds. Okay, that's the amount of radians that we do in 1 day. 1 day is 86,400 seconds. So dividing that, we will get, I'm just going to verify that in my calculator. So we got 2 times pi divide 86,400. And I get precisely the same answer. So we get 7.27 times 10 to the negative 5. radians per second. Okay, I'm not sure why that's to the power of -7 instead of to the power of -5. You would expect, because we have to the 8 times 8.654 times 10 to the 5. That would become 10 to the -5. Yeah, I think the magnitude is wrong, because 2 pi divided by 86,400 is certainly to the power of -5, so I'm going to need to mark that down. But this would be the angular speed of the Earth. This would be the procedure, so you take the actual how many rotations it has, divide that by the time that it takes for one rotation, and you'll get this. So it's just one full rotation, 2 pi, divided by the amount of time in one day, 86,400 seconds, and that should give you this number, to the power of -5. That's so strange how they got to the power of -7, but I made mistakes too, so things happen, as the old saying goes. And due to this rotation, it's asking us, how does this rotation affect the shape of the Earth? So as you spin faster, things that are farther away from you will try to get even farther away from you. I mean, think about this, like you ever had like a wet mop and you've done this and you can see like the water trying to splash off? The similar type of thing happens with Earth. So Earth is a little bit more chunky towards the equator, more thick, because things are trying to expand towards the Earth. Like try spinning, and your arms, like if you're spinning really fast, ballerina style, woo, your arms kind of have like a tendency of wanting to fly out. Like you can feel the force. Like have your arms spread out and you're spinning, you can recognize that it takes effort to bring your arms in. And the same type of thing is happening with all the oceans on Earth. Water is gonna go more towards the equator, because as the Earth's spinning, it's like it's kind of where it's trying to go. It's trying to go in a direction perpendicular to the axis of rotation. So the axis of rotation is, let me make my camera a little bigger. So the axis of rotation, let's say we have this water bottle. So you see this water bottle is spinning like this. So the axis of rotation is going to be the line at which it rotates through. Or it's like if what was spinning was like a wheel, the axle would be the axis of rotation. Okay, so yeah, on your skateboard, the axis of rotation of your wheels is going to be your truck, of the truck of the skateboard. Yeah, so everything, when something's spinning, things try to go in the perpendicular direction to the axis of rotation. So the axis of rotation of the Earth is straight up and down through the north and south poles, almost like there's a pole going through it. See, things are going to try to go in a perpendicular direction outwards from it. Okay, so that would be why Earth is a little bit more thick towards the equator and a little bit more thin towards the poles. Like here in Canada, the radius to the center of the Earth is smaller than it is in a place like Ecuador or Congo, places that are really close to the equator. Ecuador is probably the closest place to the equator, but there's a lot of countries that are going through there. Geography is cool, but the above solution is good. Also means that gravity is going to be a little bit weaker in places that are farther from the equator, because gravity is dependent on the radius to the center of the Earth. So you'll be a little bit lighter in a place like Ecuador or the Congo, and you'll be a little bit heavier in a place like Alaska, northern Canada. Yeah, and think about the gravitational equation, and it's quite a good thing to think about. Okay, so the next question that we got on the menu today is asking us, according to the lab manual, I don't know what the lab manual, what lab manual they're referring to, but we can still handle this question. Clockwise torques are taken as plus minus, and counterclockwise are taken as positive minus. Okay, so this is generally going to be the case for two-dimensional systems. 2D systems. clockwise and counterclockwise are defined as either plus or a minus. Okay, now what I would suggest is that we follow the right hand rule. So let's follow right hand rule. Okay, suppose we have like an XY axis. Here would be our Y in the vertical, and here we'd have our X. And you know, if we take our right hand rule, we put our index finger towards X, our palms of our hands towards Y. We would see that Z is the same direction that our thumb is pointing, which is out of the screen towards our face. So maybe I'll draw that like here, Z towards us. Towards us, out of screen. Okay, now the axis of rotation should also follow right hand rule. So your fingers are going to curl the same direction that it's spinning. Like your fingertips are like kind of like the arrow pointing which direction you're spinning, and your thumb is going to tell you which direction the axis of rotation is. So suppose we have a this type of situation. Our axis of rotation is going to go up. Hopefully there's no ambiguity on where that is. So this would be counterclockwise from the top. CCW from top. And if we were going the other direction, our axis of rotation would be down. So clockwise from top. Okay, so let's say that we have a situation like this. So we have we know that our Z is like coming out of the screen pointing at our face. So suppose we have a situation like this. I'm not going to draw the Z axis, but we want to imagine that it's there, and that's going to help us define our stuff. Okay, suppose that we have an arm here, and we're going to apply a force to it here. We know that the torque, let's say that this is R. We know that the torque, the result of this torque, is the tau, is going to be the F cross product with, I think it's actually R cross product with F. Some people may put it the other way around, but this is the way that I learned when I was when I'm in school. R cross product F. So in this case, you see how it's going. You see how if we were to actually implement this in real life, we would see that this is like the arm R is kind of trying to be forced into a counterclockwise direction. Okay, because of that, like you know, we're going to use the right hand rule. Our fingertips are following the arrow, and you can see as we're trying to push it counterclockwise, our thumb is pointing in the positive Z direction. So with this as our definition, so torque is a vector. Torque in positive Z direction. So in this case, counterclockwise should be positive. Okay, and if we had another example where we are going the other direction, so maybe if we draw another thing like this, our y direction here, our x, and let's say that this is our r, and we're sending a force this way. So now we're going in a clockwise direction. You know, following the right hand rule, the clockwise direction is pointing our thumb into the page, negative z direction. So clockwise is negative. So this is our right hand rule, out of page. This is right hand rule, into page. Now, sometimes it really doesn't matter if you choose positive or negative for counterclockwise or clockwise. You can use either one for two-dimensional situations as long as you stay consistent with them. But it's better to follow these conventions, because using these conventions, you're more well suited to move into 3 dimensions, and you're not going to need to change anything. You just need to follow the right hand rule. So the actual equation for torque is, I would really prefer to see it as R cross F instead of F cross R, because that like switches the direction of all that. But yeah, counterclockwise generally going to be positive, clockwise going to be negative. Even as kind of backwards as that may feel, because we like to think of positive things as things we're more used to, or we're more used to clocks going clockwise. But you know, as we see, the right hand rule is going to be more powerful, and we're going to use the right hand rule to define our positive or negative direction. So yeah, just make sure that your fingertips, so if we have like this, we're going to have, you know, this are going to be our fingertips. Fingers follow rotation, and thumb points to axis of rotation. Axis of rotation, direction. Okay, cool. I know hopefully your hand doesn't look like that. Hopefully your thumb is not significantly longer than all of your other fingers, but you know, you kind of get the gist of it. Okay. Better to have torque equals R x F instead of F x R. Explanation of the right hand rule and how following that convention would be good when moving into 3-dimensional situations would help enhance this answer. 3-dimensional. Okay. So the next question that we got is a nice multiple choice type of question. And it's asking us, a constant net torque is applied to an object. Which of the following is not going to be constant? So we have the angular acceleration, the angular velocity, the moment of inertia, and the center of gravity. Okay, so it's asking which one of those 4 is not going to be constant. But first, let's rewind for a second and let's unpack some of the first couple of words of this question. So a constant net torque. What is a net torque? So net torques these are kind of similar to net forces, or analogous to net forces, but for a rotation, but for rotational movement instead of purely linear movement. Okay, so if someone has a top or like a dreidel, a spinning thing, it slows down because there's the torque applied from friction that slows it down. So anything that changes the rotational speed, this will change the rotational speed change the rotational speed proportional to the moments of inertia. Okay, so a way that we can write this is torque is equal to moments of inertia, so that's I for inertia, moment of inertia, multiplied by angular acceleration. Another way that we could write angular acceleration is, final velocity minus initial velocity over the time that those velocities are non-constant. Okay, so which of the following is not going to be constant? Well, angular acceleration, that's kind of got to be constant given a constant net torque. This equation always needs to hold true. So if net torque is constant, moments of inertia is a physical property of the thing that's spinning, so that's going to be constant as well. And I guess that disqualifies C from our answer. Moments of inertia is like how hard is it to spin something. So for me, spinning this pencil like this, kind of like a drill, that's very, very easy. But maybe slightly harder is the moments of inertia when I spin it about this axis, kind of like a helicopter blade. And try this at home. If you got like those broom handles that are adjustable in length, try spinning it like a helicopter when they're short and versus try spinning them when they're long. It takes a lot more effort to spin something that's really long, like a long broomstick, versus like, I don't know, a spatula, something that's shorter. It's going to be a lot easier to spin a shorter thing. So that's moment of inertia. It's basically how difficult it is to spin something. It's kind of related to mass, or it's analogous to mass. So you know how force is like, things with higher masses require more force to cause an acceleration. Same thing here. So a thing with a big moment of inertia is going to need a bigger angular acceleration to cause it to start spinning. Okay, center of gravity, that's also going to be fairly constant because that's dependent on the actual material properties of the thing that's spinning. So that's not going to be affected by net torque. Angular acceleration, given that moment of inertia is constant and torque is constant, angular acceleration has to be constant. So the only thing that's going to change is the angular velocity. Okay, so if you're applying a torque, you're making something change its angular velocity, and that's what happens when you apply a torque. So it's just got to be angular velocity, and yeah, so keep that in mind. Torque changes angular velocity. Torque changes angular velocity. Ain't that a beautiful thing? Yeah. So anytime you start spinning, you're giving yourself a torque. Anytime you stop yourself from spinning, you're also giving yourself a torque, but an anti-torque that's slowing down your angular velocity. So yeah, the above solution is good. Beautiful. Okay. So the next question that we got on the menu today is asking us if the density of air is 1.3 kilograms per cubic meter at sea level. From your knowledge of air pressure at ground level, estimate the height of the atmosphere. a simplifying assumption, take the atmosphere to be uniform density up to some height, at which the density rapidly falls to 0. Okay, so let's unpack what the question has told us already, and then we can see what we can do in response to it to come to a conclusion on how to answer this question. Okay, so the density at air level, let's call that P for density, or I mean, never mind, D. Wait a minute. I don't even use the density. So okay, so the equation that we were using here is the variation of pressure with height is given as this. Of pressure with height, and this is an approximation. Okay, so is given this equation, and we have P is going to be the density, so the pressure, so it's going to be like this. So final pressure is equal to initial pressure multiplied, or not multiplied, subtract the P for density, these are both pressure values. It's going to be minus the density and multiplied by gravity multiplied by the change in height. I think it'd be better to say the change in height. Yeah, so this is the gravity acceleration, and this is going to be change in height. Okay, so so the question tells us that our density, our P, our italics P, you know, I know that we use density with P because D is already used for like distance and displacement, but you know, it leads to problems like this where we have pressure and density in the same equation, and it could be a little bit confusing. So just make sure that you draw your density P's as like clearly different. I like to draw them like very italics to make it clear that they're different. So this, in this case, our density is 1.3 kilograms per cubic meter. Our G, our gravity acceleration, is 9.81 times, whoops, not times, that's just meters per second squared. Not cubed, squared. And our H value is our change in height. This is to solve for. Okay. Nice. So, the reason why this is an approximate relationship equation is because we are assuming that the atmosphere is going to be uniform density up to some height, and then the density is just going to rapidly fall to 0 afterwards. Now, that's not exactly what the atmosphere does, but using that approximation is how we can come to an equation like this. Okay, so our the final pressure, our P final, this is going to be 0 pressure. Yeah, and I think our initial pressure is going to be, this is the sea level air pressure. So PO is equal to 1.013 times 10 to the 5 pascals. Pascals is newtons per cubic per meter squared, I believe. Yeah. Okay. So this is our values, and then we just got to solve for h. So, whoops. Let's do some algebra so we can subtract. So P final is equal to 0. Or, okay, let's actually do all of the algebra before we sub in our number. So we know we have P final is equal to P initial. Let's move these three terms, like the PG delta H, to the right side. Let's move P final to the left, to the right side. Okay, so we have, let's actually remove this. So we have P initial minus P final minus P final equals density G delta H. All right. Okay, and we got to isolate H because that's the only thing that we don't know. We're looking for, we're looking to the height of the atmosphere. So we're going to divide both sides by density and gravity. So P initial minus P final over density G is equal to delta H. Our initial is 1.013 times 10 to the 5 pascals minus 0. Because that's our final pressure that we're going to keep track of. And our density value was 1.3 kilogram per cubic meter. Multiply that by 9.8 meters per second squared. And we will come to the answer. So this will be our delta H. And let's ask our calculator what that is. 1.013 times 10 to the power 5. Divide that whole thing by 1.3 times 9.81. And we get an answer that is wildly different from what they got. So my calculation was 7,943 meters. Interesting. And that is not 10 kilometers. This is 7.9 for 3 kilometers, which is not 10. Yeah, so this would be our final answer from what we calculated here. We used the same procedure and the same numbers, so I'm not sure how they came to 10 kilometers, but yeah, but okay, you can see how we just used this equation, did some algebra, plugged in the right numbers, and we came to the right conclusion of 7.9. So the calculation is incorrect. Should result in around 7.9 kilometers. Also unsure of derivation of the equation used would be helpful. Other equations also exist for pressure at different heights, and it would be good to specify why choose this one over the other equations. Okay, so the next question that we have on the menu today is asking us how do we write 2.5 as an improper fraction? Okay, so 2 and 1/2, and we want to convert this to an improper fraction. So an improper fraction is where we have a over b and a is more than b. That's the definition of an improper fraction. And we also have a divided by b is more than 1. So that's the definition of an improper fraction. So to convert this into an improper fraction, we know that we can just do it this way. We want to convert that. We know that 2 is the same as 1 plus 1. Or we can like break this down into like the addition of terms. So this can be like 2 plus 1/2, which is equal to 1 plus 1 plus 1/2. Now what does 1 equal? If we want to make them all, so we want to make all have same denominator. Have same denominator. So 1 is equal to 2 over 2. So we can just have 2 over 2 plus 2 over 2 plus 1 over 2. And, you know, this is real straightforward. We can just, since all their denominators are the same, we can add up the numerators. So we'll just have 5 over 2, which is equal to 2 and 1/2. Now, are they equal? 5 divided by 2 is equal to 2.5. Which is equal to 2 plus 1/2, which is equal to 2.5. So this would be a fairly straightforward way to convert this particular example into an improper fraction. But in general, so let's say we have general conversion to improper fraction. Not fraction, not faction, fraction. So suppose we have like a and then b over c. This is going to be equal to a times c plus b over c. Okay, so the example that we had, of course, we would come to the same conclusion, but maybe we have like 27 and 3 over 7. This would be equal to 27 times 7 plus 3 over 7. 27 times 7. 189 plus 3 over 7. That's 192 over 7. And we can see that 192 over 7, 192 divide 7. This is equal to 27.428 on and on and on. We know that this is 27 plus 3 over 7, and 3 divided by 7 is 0.4285 on and on and on. And you can see that these are absolutely equal. Okay, so in general, this general form for conversion into improper fractions is always going to work out, and it's going to be a lot easier than trying to break it down. Okay, and yeah, so the above solution is correct. Answer could be enhanced with a general form equation that is always right with variables. With variables for the with variables to sub in. Okay, so the next question that we have on the menu today is asking us what are the charges on plates 3 and plate 6. And this is a circuit where we have capacitors in series. Okay, so let's first talk about capacitors for a little bit and see what would be really going on here. Okay, so capacitors. They look like this. They are two plates that are separated. They are two parallel plates. And when charge accumulates on one, the equal and opposite charge is going to accumulate on the other plate. So let's say we've got like plus, 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 plus. We have 4 plus charges on the left side. We're going to have 4 minus charges on the right side. Okay, so I'll write that as a rule. The charge on one plate of the capacitor is always equal in magnitude but opposite sign as the other plate. Okay, so let's say here we have 4Q. Here we would have negative 4Q. Okay, so that's exactly what would be going on here. So let's kind of use these rules and look at the circuit and see how we could incorporate that stuff together. Okay, so we don't really need to draw the sources. So it's saying here we have a positive Q, and this is 1, and this is 2. So based on the rule that the other plate has to have the same, we know that this has to be negative Q. Okay, so this is yeah. Okay, and I'm going to assume that these numbers are to specify the capacitor numbers, and they're not actually saying like this has more capacitance than the others. But it would be like the same principle because the amount of charge is obviously going to be constant, and even if they were different capacitance values, I'm pretty sure that this wouldn't really change the way that this question is solved. Okay, so keep in mind that this section here, so this is plate 3, and this is plate 4. I'll just draw out the whole thing. This will be plate 5, plate 6, and I might as well just draw the whole circuit. So here we have the positive terminal, here we got the negative terminal, and this is delta V. Okay, so if we have a positive charge on the thing here on the right hand plate, we're definitely also going to have a negative charge here, because as much as this voltage source is going to want, like assuming this is a DC voltage source, as much as it's going to want to push current through here, it's not going to be able to. But the best that it can do is put some positive charges here, or it's going to like try to shift the positive charges from here, from 6, and they're going to move those positive charges all the way over to 1. So because we have positive Q here, we're also going to have negative Q on 6. All right, and so let's another thing that we can do is we know that the total charge in the section, the 2 plate, the wire, and the 3 plate, that has to have like an overall net charge of 0, because these are really not even in a circuit at all. In a DC, these parts are like disconnected, but charge is still gonna like accumulate on one side. So for the negative charges to accumulate here, it has to also that means like electrons from plate 3 are moving towards plate 2. That means there's a lack of electrons on plate 3, which means that we're going to have a positive Q on plate 3. And because of that, we will have a overall net zero charge in the 2-3 area. And you know that the charge opposite to the plus is always going to be the same but negative, so we're going to have negative Q. And for the exact same reason that we have positive Q on 3 and negative Q on 2, the same type of pattern is going to happen for 4 and 5. So we're going to have positive Q on 5. Hey, and it seems like the circuit has to be happy at this point, because we're still following the rule that the plates are going to have equal and opposite charges from each other, and everything would seem to work out. So the charges on plates 3 and 6, 3 is going to have a plus charge, so let's just circle that because that's like one of our answers, and the 6th plate is going to have a negative Q charge. Okay, and yep, so the capacitors in series always have the same charge across them, regardless of their capacitance values. So even if C, 2C, 3C, if those are capacitance values, it doesn't really matter. We're still able to come to the same conclusion because the rule still stays true. The Q value for series capacitors always the same. And yeah, so charge, we got positive Q on plate 3 and negative Q on plate 6, and that is all because of the fact that we have the source here is doing the negative Q, but then again we're also following the rule, and in multiple, no matter which rules that you choose to start with, we will always come to the same conclusion that all these plates going to have the same charge of positive or negative Q. Positive if you're if you're closer to the positive terminal of the source, and negative if you're closer to the negative side of the source. I think that's fairly straightforward. So yeah, this is awesome. So the above solution is good. Oh man, that was my last question. Time flies when you're having fun, as the old saying goes. Yeah, switch my view real fast. So those are all the questions that we're going to cover today. If you enjoyed today's Q&A and would like to be notified of when we do this next, please hit the subscribe button and ring the notification bell below. If you would like to submit your own questions, take a look at the links in the video description, and remember to leave a like if you really like the video, and leave a comment telling us how you feel about it. If you really like the video, share this video with your friends. And this has been Millan from OneClass. I hope to see you again soon. And remember, physics is always a good time. Never, ever doubt the physics. You'll always have a good time when you do it. And have a great day, and enjoy the rest of your night. Well, it's night for me, but it might not be night for you, but, enjoy your day. Take care.